We here present a tool for fast dynamic circuit behavior analysis to enable better than the worst case circuit design. We need to first introduce the timing speculation concept. Timing speculation is a mechanism for better than worst case design by observing that some paths are frequently exercised and some paths are rarely exercised. If we deliberately allow timing error to happen with a higher probability of producing correct result, we can achieve a higher throughput for a circuit. One mechanism to tolerate timing error is by using radar logic which detects the timing error. If timing error is detected in a pipeline CPU design, it may require the flush of the whole pipeline stage. Another mechanism to tolerate timing error is by using telescopic unit, which predict the timing error and prevent it by allowing multi-cycle computation. No matter which mechanism is used for timing error tolerance, we can generalize it to a uniform formula. From this formula, we observe if we can reduce the cycle time and increase the probability of getting correct result, we can achieve higher throughput. We need first to compute the circuit dynamic behavior by varying the cycle time. At each specified clock cycle, we need to compute the probability of getting correct result. This is done by using the characteristic function and the timed characteristic function by recursively call the TCF function until reaches the primary input. With any given circuit, we can compute the TCF function as a function of primary input and cycle time, and then we represent this TCF function as a BDD with the probability back annotated. And then on this BDD, we can compute the probability of producing correct result at the specified timing point t. To avoid the construction of a huge BDD, we want to calculate the probability in a partitioned manner. This can be done by using timed tenor decision diagram, and each input of the partitioned circuit is regarded as a timing graph with 3 stabilization status at any given point t, and each stabilization status is associated with a probability. First, we construct the timing decision diagram, and then from the input of the sub-circuit, we back-annotate the probability from the input behavior graph. And third, we compute the probability on the timed tenor decision diagram. We can relate the throughput with the frequency. Traditionally, we clock the circuit with the longest critical path delay, but if we can overclock it to a certain amount, we can achieve a higher throughput. Dynaton can further extend the throughput by lifting the behavior curve. Which in turn enable us to overclock the circuit deeper. That's translated to an extra throughput gain and extra frequency gain. Lifting the behavior curve is achieved by iterative optimization. At each iteration, we find the max flow mean cut of the nodes which contribute the most to the probability. We also keeping a moving average to rule out those nodes in the cut set but contribute relatively small. We carry out the study on a module extracted from the Leon 3 bypassing logic. The Synopsys design compiler can optimize this module regardless of the frequency of using each individual input. Traditionally, we can clock the circuit at 340 picosecond. With time speculation, we can overclock it at 315 picosecond, with a probability of 94% of producing critical result, which turns into 5% of throughput gain. If we use DynaTune, we can targetedly optimize the circuit for those most frequently exercised passes. This enables us to clock the circuit at 270 picosecond, with a probability of 90% producing critical result. This in turn gives us 20% of overall throughput gain. In our experiment on MCNC benchmark, DynaTune enables us to achieve 20% of throughput gain on average, or 32% of frequency gain on average. In effect, DynaTune transforms 60% of frequency gain into a throughput. To conclude, DynaTune exploits the probabilistic information of a circuit during optimization, and we proposed a way to derive dynamic behavior of a circuit, and we use the behavior curve to guide the optimization, which effectively improves the throughput for time speculation.